Welcome back. In this lecture, I will start a new topic, fugacity in liquid mixtures. So, let me just write down first a generic expression of the fugacity in liquid phase is written as gamma I times xi times Fi0, okay, and Fi0 is a function of T, P and some concentration or mole fraction. So, gamma I is nothing but activity coefficient, whereas this Fi0 is a fugacity of I at a standard state. Okay. Now, it is important to understand that gamma I and Fi0 are interlinked. Okay. So, as we know that gamma is equal to 1 when solution is ideal. Okay. Now, however, gamma equal to 1 can have a different interpretation. That means the ideality depends on the reference state, and thus it's important to understand that whether this reference is with respect to dilute conditions or in general it is in a Raoult's law sense. So, something which I am going to elaborate now. So, that is, this can be ideal in the Raoult's law sense or Henry's law sense. So, what I am going to do is I am going to define formally the ideal solution. So, at a constant temperature and pressure, the fugacity of every component in an ideal solution in an ideal liquid solution is proportional to the mole fraction. So, that is what the definition of ideal solution is. So, in other words, what we are saying is that FIL is equal to some proportionality constant Ri multiplied by Xi, which holds for Xi from 0 to 1. Okay. So, note that Ri is just a function of temperature and pressure, independent, and it should be independent of Xi. Okay. And if gamma I is equal to 1, which essentially means Ri is nothing but Fi0, that is what we have written here. Okay. Now, for the case of large range, it is, that means when typically the I is large, then it turns out to be Raoult's law kind of sense, but when Xi, that means the concentration of the solute is extremely small, still you can define ideal solution. Okay. So, that means if Xi is close to 0, it is still possible to have an ideal solution. Now, such solution is with reference to the Henry's law. So, this leads to the Henry's law. Okay. So, I will come back to this in a bit, but let me now consider the case for 0 x 1. Okay, in that case I can write FIL as a function of TP xi as simply xi FL pure I TP. Okay. So, that will be the case for the Rawls law point of view. Now, what I am going to do is I am going to connect this to for the case, I will try to use the expression of Gibbs-Helmholtz equations, and from there I will try to connect the logarithmic form of Fugacity to enthalpy and molar volumes. So, what we have from the Gibbs-Helmholtz equations is the following. This is something which we have looked into for the pure fluid. Okay. So, I am just reproducing this. So, for the case of the mixtures, this is going to be Vi bar. Okay. And this is something which we can now make use of it for the case of what we are looking at. Okay. So, I am going to apply these Gibbs-Helmholtz equations. Since mu we have defined in terms of the fugacities, mu I minus mu I 0 is equal to your RT ln Fi by Fi 0. So, if you use those expression directly, and so you can replace d mu or mu in terms of that, and then the derivative would turn out to be with respect to the fugacity. Okay. So, using standard relation of mu and f, I can now write, I can plug in here, okay, and I can show that without going to derivation, I can show that del ln Fi by del t Px is nothing but minus of Hi say 0 by RT square. Now, this is something which you can show yourself. Okay. Now, remember that for the pure fluid we have del ln F pure I del T P is equal to minus of small Hi 0 by RT square. Here for the case of mixture you have partial molar enthalpy. In case of the pure you have simply molar enthalpy, and this is with reference to reference. So, when you are going to use this mu I, there is a reference mu I, and that will give us this information. Okay. So, you can derive this without, so you can derive it at home. I am not going to go into the details of it. I can also write this for the case of this, where the partial derivative is with respect to the pressure. For the case of the pure fluid, this would be simply Vi by RT. Okay. Now, this is the partial molar enthalpy of I, this is your partial molar enthalpy of the reference state, which is basically the ideal gas, let us say at T. So, Hi bar is nothing but partial enthalpy of I. Similarly, Vi bar is partial volume here of I, and small Hi is molar enthalpy of pure fluid, and Hi 0 or Vi 0 is basically molar enthalpy of an ideal gas or reference state at T. Okay, ideal gas state at T. Okay, so this is something which I have written without going through the rigorous derivation, but I believe that you can do that knowing the relation of mu and fugacity. You can plug in all this and come up with the derivation. So the question is why we are doing this. Let us come to that. And now I am going to do is I am going to consider for the ideal solution what would be the del log of I as a function of with respect to the derivative of log of FL with respect to T at a constant Px. So what is that for the case of ideal liquid solution? So I am going to consider this, and here since this is your ideal solution, I can replace FL IL as F pure, okay, multiplied by Xi, okay, and since this is at derivation is sorry, this differentiation is with respect to T, keeping P and X is equal to constant. So essentially I can write this as d ln F L pure and del T at P. Okay. Alright, so now this, if you look at it, del F by del T is nothing but Hi bar minus Hi small hi 0 divided by RT square. So this essentially means this should be minus of Hi minus Hi 0 by RT square, and on the other hand this is a pure fluid, this should be Hi minus Hi 0 by RT square. Now this must be same, this implies that Hi bar is equal to Hi for the case of ideal solution. Okay, similarly you can show that for the case of ideal solution Vi is equal to Vi. So earlier we have done this exercise for ideal gas mixtures. Okay, now we are looking at liquid solution, remember that, and in liquid solution you have the this kind of property, okay, for the case of ideal conditions. Okay, so what does that mean? It by obtaining this you can conclude that for an ideal solution, ideal liquid solution, mixing takes place athermally, because that Hi bar is equal to Hi, which essentially means delta H mix should be 0. Okay. Similarly, upon mixing for an ideal liquid solution, it should not have, or it should not change its volume. That means the mixing takes place without change in volume, which means delta V mix is equal to 0. So this is the statement directly from this expression. Now other statement which I am going to make is that the real fluid, of course, do not exhibit ideal mixture, okay. So though real fluids do not make form ideal mixture, but if the similar fluids of similar kind, similar molecular nature, if they are mixed, they behave more like ideal liquid solution. Okay. So but similar liquids exhibit close to ideal behavior. Now other important thing is that all solution of chemically stable non-electrolyte, this is important, behave ideally in the limit of infinite dilution, which essentially means that if the solution is extremely dilute, then they will start behaving like an ideal solution. Okay. So, how do you represent deviation from the ideality? If the solution real fluid does not behave like an ideal solution, then there is a deviation from the ideal solution behavior. So, we make use of excess function. I am going to define that. So, the correction term is given in terms of excess function. Okay, that means for any extensive property, let us say E, I am going to define excess function as ETPN with respect to EIS TPN in a similar way where we define for the gas mixtures. So, for the solution also I am going to define it. Now, as we have already discussed earlier, that for any excess function, you can make use of the standard relation of the enthalpy or in general thermodynamic functions, and the thermodynamic function in terms of excess function will hold, such as for example this. Okay. So, this holds. Okay. Now, usual relation of the derivative also holds, for example this. Now, one of the most important thing in this excess function is basically G excess gives free energy. Now, this, if it is greater than 0, it shows that it is a positive deviation from ideality. If it is less than 0, it shows that negative deviation from ideality. Okay. So, it's both ways. So, when you say negative deviation from ideality, which means basically G excess must be less than 0. Okay. Partial molar excess free energy, partial molar excess quantity. So, it is EI x, and this is nothing but del EI x divided by del Ni Tp all other I constant. Okay. All other, let us say J constant, such that J is not equal to I. We know from earlier expression or earlier lectures that E is nothing but summation of Ni Ei bar. Similarly, Ex would be summation Ni Ei excess, okay, bar. So, this is something which we have done this exercise. So, the most useful for our analysis of the liquid mixtures and its property is nothing but G I partial molar excess gives free energy. So, Gi bar excess, okay, because this gets reduced to gamma, it is connected to gamma, which is activity coefficient. So, let me now talk about this activity coefficients and try to connect with this Gi excess. Let me formally define activity and activity coefficient. Okay. So, activity is defined as AI, which is basically nothing but the ratio of Fi Tp Xi with respect to Fi0, Tp some reference state pressure Xi0. So this is basically nothing but arbitrary, but must be specified. Okay, and Ai is nothing but Uxi gamma I. Okay, so in other words, gamma I is nothing but Ai divided by Xi. Okay, so this is something which we already know. Okay, so I am defining this here. Now let us see how we can connect this gamma I or A's to the Gi axis. Okay, so let me start with Gi axis definition, which is nothing but Gi bar minus Gi with respect to ideal solution. Okay. Okay, so what is Gi? So Gi, you can relate this Gi to mu I, and since mu I is related to RT ln Fi, you can show that this is nothing but RT ln Fi, okay, minus RT ln Fi Is, the reference part which comes here, the second part get cancelled because you are using the same reference here. So RT ln Fi Is remains here, which essentially means Gi axis bar is nothing but RT Fi Is. Okay, now you can relate this to, because you know the Is for solution for any liquid is nothing but RT Fi Xi Fi0. Okay, so this is for ideal solution. Now using the definition of Fi is Xi Fi0 gamma I, that is the definition of Fi. Okay, with respect to gamma I, so I should be able to now plug this in here, and I can write here Gi axis as RT ln gamma I. Okay. Now the next thing which we would like to do is to make use of the fact that Gi axis is summation Ni Gi axis this. If you divide by n, I get n here, and this is nothing but small g axis, molar axis gives free energy per particle, and this is nothing but, if you use Gi axis as this, then becomes RT summation Xi ln gamma I. So we got an expression of G axis as RT summation Xi ln gamma I. Okay, all right. Okay, so now what is the next thing which we can do? So we got an expression of molar gives excess free energy with respect to the activity coefficient. Now let us consider Tp derivative of gamma I. Okay, so consider the ideal consider reference state for ideal solution from the sense of Raoult's law. Okay, so this is in the sense of so I can write gamma I as FIL Xi FIL pure I. Okay, so when you consider this, we use this Fi0 as nothing but FIL pure I. So essentially means I can write ln gamma I as ln FIL, okay, TPX minus ln Xi minus ln FL pure TP. Okay. Now we know the expressions of the derivative of Fugacity So, for example, if with respect to T, then this should be P, and this is nothing but minus Hi bar minus Hi 0 by RT square. Okay. So, what we can do is we can use this expression. So, you have now expression of ln gamma I, ln Fi. So, you can take the derivative of log of gamma I with respect to temperature at a constant pressure, and this is the right hand side. So, you can also make use of that, and now from here, given this expression of Gibbs-Helmholtz expressions, you can directly connect this the logarithmic to the partial molar properties such as enthalpy. Okay. So, I will try to show this. So, let us say this is what we want, the derivative of log gamma with respect to temperature at pressure and x. So, this is going to be, you can show, I am not going to get into details of that. So, you have to take the derivative of this, which essentially is Hi minus Hi 0, this is going to be 0. You have to take the derivative of this also, which is nothing but small Hi bar minus Hi 0, and since this is at constant temperature. So, since it is a given temperature, the Hi 0 will cancel out. So, what remains is nothing but the following. Only Hi will remain. Okay. So, this will be minus Hi E by RT. So, excess Hi. Similarly, you can show that gamma I by del P by at a constant Tx is nothing but Vi bar Tp x minus small Vi Tp for the pure fluid, RT square, here it will be RT here, and this will be nothing but Vi excess by RT. Okay. So, this is by considering the Raoult's law sense. Okay. Now, for the case of dilute ideal dilute reference state, if you consider and apply the same expression what we have got here, then if you apply the same relation which you have got here for the case of the system where one particular solute has a critical temperature much lower than the temperature of the system, then we have a serious problem, because typical mixtures will not occur in the liquid state at that particular temperature. So, in that case we have to worry about whether we should use the Raoult's law sense of reference state. So, in such case ideal dilute reference state can be considered. So, this is useful whenever liquid mixture do not exist over the entire composition range. Okay, so for a given temperature, one of the fluid may remain as a liquid in the pure state, but other one may not. It may remain in a supercritical state. So, by considering a Raoult's law sense, which essentially is valid when the system remains in a liquid phase from 0 to 1 composition, then in that case you have to come up with a kind of fictitious reference state if you want to use a Raoult's law for as a reference state from the Raoult's law sense. So, we need to change a different reference state, and that is what the ideal dilute reference state comes into the picture. So, as I was saying that if you consider a liquid mixture containing gaseous solute, okay. So, in such case let us say this is the scenario that critical temperature of the solute, which is 2, is much less than T of the system. This implies that a liquid phase cannot exist as composition of two approaches towards one. Okay. Now, if you want to use the Rawls law based reference system, and then the relation which we have developed here for the gamma, okay, in order to achieve this we must have come up with a hypothetical standard state for state 2 at that particular temperature. Okay, so therefore, relation based on the sense of Rawls law can be used only after introducing a hypothetical reference state or standard state for solute 2. Okay. So, this is why in such a scenario it is more convenient to consider ideal dilute reference state which avoids this kind of difficulty, and that is why the Henry's laws comes into the picture. Okay, so let me write that. So, consider in this such case we consider x2 is very small, okay, and in that case the Henry's laws states that F2 at Tpx, this approaches towards 0, this fugacity of 2 approaches towards x2 H21 Tp, okay, where S21 is Henry's constant of solute 2 in solvent 1. Okay. So, going back to the original definition of the fugacity which we came up here, if you look at this expression, okay. So, what would be R2 in this case? Okay, R2 would be F2L divided by x2, where x2 approaches towards 0. So, therefore, R2 is equal to limit F2L divided by x2 at x2 approaches towards 0. Okay, and this is nothing but H21 Tp. So, this is a Henry's constant of solute 2 in solvent 1. Okay. In contrast, what would be R1? So, R1 is basically that same R, but for the solvent. So, for solvent we will be considering limit F_L divided by x1, where x1 goes to 0, and this will be in the sense of Rawls law. Okay. So, this is what is very clear, that when you have a system like that where you may have to consider two different reference states, one for different for solvent, one for solute. So, I will come back to this in the next lecture and elaborate more on this, and particularly other concepts such as normalization. Okay. So, I will see you in the next lecture.